Okay, welcome everyone. I'm really sorry about the delay, but I'm very excited to share today's talk with you. My name is Jiang Hu, and I work at UCLA Office of Advanced Research and Computing, OARC. Today, we will be diving into a very hot topic, neural networks. As many of you know, neural networks are at the heart of today's artificial intelligence boom. There is no really need to elaborate on their importance beyond the two pictures I've included here. This year's Nobel Prize alone highlights just how significant the neural networks are. For instance, the Nobel Prize in Physics celebrated John Hopfield and Jeff Hinton for their groundbreaking work in neural networks, while the Nobel Prize in Chemistry recognized DeepMind's AlphaFold for its advancement in protein structure prediction. For all of us as general users, tools like ChatGPT, Google's Gemini, and Anthropic's Cloud have become indispensable in our daily life. Even if you are an open source enthusiast, you will probably notice the excitement around Meta's Llama model. Looking at things from a different angle, if you have been following the stock market, it is impossible to ignore NVIDIA's meteoric rise. Within a year, it has become the world's most valuable companies, even surpassing Apple and Microsoft. This incredible growth is all because of its GPUs, which are still the number one choice for accelerating neural network computations. So, I believe today's topic will be both timely and fascinating. First, let me outline what I will be covering in this talk. I will structure my discussion around four key questions. First, I will start with an introduction to neural networks, what they are and how they work, keeping it brief and straightforward. Then, we will dive into the technical details and uncover some of the magic behind it. Next, I will explore why neural networks are so powerful today. We will reflect on their strengths in computational science and artificial intelligence. Finally, I will discuss what lies ahead beyond the conventional approaches to modeling neural networks. This includes thinking critically about potential advancement and opportunities. Before we begin, here's a quick disclaimer. This talk is designed for an introductory audience. My focus will be on the concepts rather than the mathematics. So there won't be any code examples or demos, no Python, no PyTorch. Instead, I encourage you to sit back, enjoy the discussion, and engage in some brainstorming. I also want to mention that I'm really looking forward to your feedback. Our organization provides technical support and consulting, and we are always eager to explore collaborations opportunities, especially within the UCLA community. I'll share a survey link in the chat later. If you have to leave early, feel free to drop your questions or feedbacks there. You can also suggest topics you would like us to cover in future sections. Your input is always welcome. So let's start with the first question. What is a neural network? I want to begin with a physical science perspective. Traditionally, we extract knowledge using our brains by analyzing data, generalizing patterns, and developing theories or rule-based algorithms. This workflow is often used to make predictions. There's also another approach that takes things a little bit further, where we extract routines or rules directly from data using techniques like feature extraction, support vector machines, or other statistical-based data mining methods. This allows us to learn specific algorithms without explicitly defining them beforehand. Neural networks, however, goes even further. Unlike those traditional methods, neural networks don't require prior domain-specific knowledge to be coded into them. Instead, they learn patterns directly from the data and use those patterns to make predictions. It is as if we are asking machines to develop a form of intelligence on their own. The essence of neural networks lies in their unique structure. Different forms of domain knowledge and algorithms are embedded in their topological architectures, what we often call their network structure or connections. This provides a high-level view of how neural networks fit into the broader context of modeling and computation. As the name suggests, a neural network consists of interconnected nodes, which we call neurons. But what exactly is a neuron? Let's start with a simple example, a linear classification task. Imagine we are trying to classify data into two groups or classes. To do this, we might draw a straight line, represented by an equation involving two variables, x1 and x2. In this case, we assign one group, say the green class, to values where z is smaller than 0, and another group, the red class, to values where z bigger than 0. This gives us a dividing line, and the equation for that line helps us separate the two classes. Next, we calculate the z values for the data and use a step function to create a binary output y. Here, y equals 0 for one class and y equals 1 for the other. This creates a simple relationship between x1, x2, and y, forming the basis of the classification task. Now let's connect this to artificial neurons. In essence, an artificial neuron performs the same task as the relationship we just described, but from a slightly different perspective. We treat x1, x2 as input, and the neuron processes these input by performing simple arithmetic operations. For example, the neuron might calculate the W1 times x1 plus W2 times x2 plus bias, where W1 and W2 are weights and the bias adjusts the calculation. Then we apply an activation function to this result to separate the two classes. The output y will be either 0 or 1 corresponding to the green or red classes. This concept has a strong biological parallels. In biology, neurons are connected by synapses as they transmit information using electrical signals. In 1940s, two scientists, Warren McCulloch and Walter Pitts, developed the MCP model to approximate this process. It is a simplified version of biological neurons, where input are weighted and summed, and an output is computed based on these inputs. The MCP model is essentially an artificial neuron, and despite its simplicity, it is a powerful building block for neural networks. While the MCP model is one way to approximate a neuron, it is not the only way. Later in this talk, I will discuss other methods for simulating or approximating artificial neurons that will extend beyond this basic approach. Once we understand the basics of a single neuron, transitioning to the concept of a neural network becomes straightforward. A neural network is essentially a collection of artificial neurons stacked in multiple layers. Let's revisit our example of logistic regression. Here, x1 and x2 form the input layer. It feeds into two interconnected neurons. These neurons process the input data to produce intermediate output, x1 prime and x2 prime. These intermediate output then pass through another layer of neurons that handle the final classification task, producing the binary output y. In this structure, x1 and x2 form the input layer. x1 prime and x2 prime make up the hidden layer, and y represent the output layer. The operations here, weighted sum, biases, and activation functions, serve different purposes. Between the input and hidden layers, the operations focus on feature information. In contrast, the final layer typically handles a classification task. In a broader data analytics, this process can be seen as transforming high-dimensional input data, sometimes with millions or even billions of dimensions, step by step into a reduced, actionable form. At each layer, transformations separate and decouple information, reducing dimensions to focus on the task at hand. While this example uses logistic regression to demonstrate binary classification, neural networks can handle a wide variety of data analysis tasks. So far, we discussed a simple two-layer neural networks. But what happens when we stack more layers? This is where deep learning and a deep neural network come in. Adding more layers allow networks to solve problems that were previously impossible. One pioneering example dates back into 1998, featuring a network with 5 layers. Fast forward to 2010, and the ImageNet large-scale visual recognition challenge began pushing the boundaries of image classification. Each year, the winner showcased increasingly deeper networks. For instance, AlexNet in 2012 had 8 layers. VGGNet in 2014 had 19 layers, and Google Inception Network introduced 22 layers in the same year. The real breakthrough came in 2015 with the introduction of a residual network, ResNet. It included a skip connection. These connections allows networks to reach unprecedented depths, such as 152 layers, while still maintaining performance. Later architectures like HighwayNet and DenseNet extended this idea, with some models experimenting with up to 10,000 fully connected dense layers. In the era of large language models, such as OpenAI's GPT-3, deep networks becomes even more transformative. GPT-3, released in 2020, features 96 transformers layers, while Meta's Llama 3.1 from 2023 include 120 transformer layers. Transformer developed by Google researchers have become the backbone of modern neural networks due to their ability to generalize across various tasks, from natural language processing to computer vision and even scientific modeling. Although we don't have time to explore the inner workings of transformers here, I hope this gives you a sense of how deep neural networks can go. Now, let's classify different types of neural networks. This can be confusing at first, so I've created a simple framework to help clarify. The first type is the feed-forward neural network, where there are no cycles in the connections between nodes. Data flows in one different direction from the input layer through hidden layers to the output layer. Examples include fully connected networks and convolutional neural networks, which are widely used for image processing tasks. The second type introduces cycles in the connections, forming what are known as recurrent neural networks. These networks allow information to loop back, making them effective for tasks involving sequential data like time series or language processing. A famous example is the long short-term memory LSTM network. Another example is a Hopfield network named after John Hopfield, who received the Nobel Prize in Physics this year. The third type, which is less popular today, is the symmetric network. In these networks, connections between nodes have no specific direction. A typical example is the Boltzmann machine, which Jeff Hinton worked on extensively. Symmetric networks are often linked to physics-based models, such as energy-based models, EBMs. These are useful for simulations like stochastic processes or spin class model in physics. In modern AI, many architectures combine aspects of these types. For instance, transformers incorporate feed-forward and recurrent components, depending on the tasks. Understanding these categories can help clarify how different neural network architectures are designed for specific purposes. So let's think about deeper neural networks as a kind of a black box. They take some input data and produce an output, and the process of building them can be understood as solving an optimization problem. From a mathematical perspective, we start with data, lots of data. Then we choose an architecture or network structure for the neural network. This architecture contains many parameters such as weights and bias. These parameters are initially unknown. For any given input, the neural network uses these parameters to make predictions. To make the network work for a specific task, we need to adjust these parameters so the predictions are accurate for our data. This adjustment is the core task of training a neural network. To do this, we compare the network's predictions to the ground truth. Initially, the difference or error between the two might be large. Through a process of training and optimization, we aim to reduce this difference to a minimum. This requires starting with some arbitrary initialization of the parameters we call theta 0. Whether these initial values are 0 or random or something else can affect the outcome, but we treat them as an arbitrary for now. Once initialized, we calculate an initial cost value, C0, representing the error. Then we apply an optimization algorithm to minimize C of theta iteratively, adjusting theta until we reach the best possible model. This is the big picture of how deep neural networks work, providing a framework for understanding their optimization process. So now it's time for us to take a closer look at what happens behind the scenes. To make the optimization process solid, here is a simplified workflow for training neural networks. We start with data. This means collecting and preparing it, ensuring it is in the proper input format for the neural network. Once the data is ready, we decide on the neural network structure suitable for the task. The structure will depend on whether we are tackling tasks like a classification, regression, or something else entirely. After selecting the structure, we choose a loss function. It measures the difference between the predictions and the ground truth. This is key to guiding the optimization process. Then we train the network iteratively, refining the parameters through evaluation and adjustment. If needed, we might collect the additional data, retrain the network, or fine-tune the model further to achieve better results. Ultimately, the goal is to find the optimal weight and biases for the task at hand. This is a simplified but a comprehensive view for the neural network training process. Let's start with the first step, data preparation. This phase often involves a significant effort and varies depending on the task. For example, the image data processing, we might scale pixel values, apply augmentations, and perform convolutional and flattening operations on the images. For natural language processing (NLP) tasks, the preparation involves organizing text data, breaking it into smaller units such as tokens, and mapping these tokens into a vector space. Since text data often comes as sequences, we also need to align and pad the sequences for consistency. At this point, I want to highlight a critical part of data preparation, embedding. Embedding serves several purposes. First, it maps a high-dimensional and sparse data into a lower-dimensional, dense vector space. For instance, text data often contains many zeros in its representation, and the embedding condenses this into a dense format. Second, it merges multi-modal data like text, images, audio, and spectral data into a single vector space for analysis. Finally, embedding preserves contextual relationships between data points. For example, in an embedding space, men and women should be closer to each other than house and chair, reflecting their contextual similarities. Various techniques exist for embedding, such as dimensionality reduction methods like PCA, principal component analysis, and NLP-specific methods like word-to-vec. In some domain-specific tasks, embedding might be part of the model training itself, a concept known as representation learning. Researchers have even approximated that the optimal embedding dimension is proportional to the fourth root of the number of possible values. This demonstrates how embedding is not just about compression, but also about maintaining meaningful relationship in the data. Data preparation involves much more than collecting data. It is about transforming and organizing it in ways that makes it ready for neural network training. This critical step sets the foundation of all subsequent processes. So once our data is ready, the next step is to apply a neural network architecture suitable for our problem. Fortunately, mathematicians have given us a foundational result known as the universal approximation theorem. This theorem was introduced by Cybenko in 1989 and later expanded upon by others in 1991. The theorem simply states that a feed-forward neural network with at least one hidden layer can approximate any continuous and nonlinear function to any desired level of precision, provided the hidden layer contains a sufficient number of neurons. This essentially means that even a very shallow network with only one hidden layer but many neurons can model any functions. Such networks are often called wide or shallow networks because they have few layers but many neurons. On the other hand, we can build deep neural networks by introducing more hidden layers. Adding more layers creates a hierarchical structure which can have several advantages. For example, a 2017 paper demonstrated that hierarchical structure often require fewer parameters compared to the wide networks, making them more efficient. These structures also help extract and build better features, which is crucial for handling complex tasks. This efficiency and feature extraction capability explain why deep architectures are so popular today. It is important to note that real-world problems are really a simple choice between shallow and deep networks. Instead, we often need to balance the strengths of both approaches. For example, modern models like GPT use a mechanism called a mixture of experts, which combines smaller subnetworks instead of relying solely on a single very deep network. This strategy can sometimes be even more effective. We might be able to have a little time to discuss this concept more in later slides. Today, we have an expanding encyclopedia of neural network architectures, each suited for specific tasks. Choosing the right architecture depends on the problem you are trying to solve. For example, autoencoders work well for unsupervised learning tasks. Recurrent neural networks, RNNs, are excellent for sequence data like time series analysis. And convolutional neural networks, CNNs, are the go-to choice for image processing tasks. In computer vision, we also see more advanced architectures such as UNet, which extends CNNs with the encoder-decoder structures for tasks like image segmentation. For sequence predictions, the LSTM long short-term memory model remains a strong choice. Some even argue that with proper design, LSTMs can outperform the reason transformers in specific use cases. Well, it comes to generative tasks. Generative adversarial network GANs are widely used for tasks like image generation. Meanwhile, transformer architecture, which are the backbone of today's large language models, have proven highly effective for natural language processing and beyond. Another emerging architecture is the graph neural network, which excels at handling data represented in graph form, such as social networks or molecular structures. Finally, diffusion models inspired by thermodynamics are becoming increasingly popular for generative tasks like video creation. For example, OpenAI combines diffusion model with transformers in their advanced system. My main point here is that while many pre-designed architectures are available, selecting the right ones requires domain knowledge and a deep understanding of your specific problem. Now, let's talk about activation functions, which are a critical component for neural networks. Activation functions determine whether a neuron fires and are responsible for introducing the nonlinearity that makes neural networks so powerful. Without them, the network would simply perform linear operations, severely limiting its capabilities. Here are some commonly used activation functions. The sigmoid function, which squishes input values into a range between 0 and 1. The tangent H hyperbolic tangent function, which maps the inputs to a range between -1 and 1. And ReLU rectified linear unit function, which have become one of the most popular choices due to its simplicity and efficiency. Variant of ReLU like Gaussian error linear unit GELU are used in modern transformer models, including Google's BERT and OpenAI's GPT model. Another activation function worth mentioning is softmax, often used in the final layer for classification tasks, as it converts outputs into probabilities. Researchers have also developed learnable activation functions, such as those used in max-out networks, which adapt dynamically to the data. Activation functions are more than just mathematical tools. They are essential to the intelligence of the network. Choosing the right activation function can significantly affect performance and make or break a neural network's ability to model complex relationships in the data. Now let's discuss an essential component of training neural network, the loss function. The loss function measures the quality of our model's prediction compared to the ground truth. You can think of it as an objective function that evaluates how well the model is performing. It quantifies the misfit of the model as a function of its parameters. The primary goal of a loss function is to minimize the error, which is often referred to by different names, such as loss function or cost function. While the terminology may vary, the concept is the same: to penalize the difference between the predicted outputs and the true labels. When applying to a single training example, it is usually called a loss function. When applied across batches or the entire training set, it is often referred to as a cost function. These terms are frequently used interchangeably sometimes. Depending on the task, there are various types of loss functions. For example, in tasks involving spatial relationships, we use vector space-based measures. These include the Euclidean distance for straight line differences and cosine similarity for angular relationships, which are especially useful for text embedding or high-dimensional data. For classification tasks, measures like hinge loss are common in methods such as support vector machines. On the other hand, some tasks involve probabilistic outputs, where we minimize the divergence between two like predicted and target probability distributions. In such cases, we often use cross-entropy loss or its variant focal loss, which is common in generative tasks like image synthesis. There are also specialized measures like the weather staying distance for comparing distributions in GANs. For binary or set-based data, domain-specific metrics like the Jaccard similarity, Sorensen dice coefficient, or Hamming distance are used, especially in fields like bioinformatics. While we don't have time to explore these in detail, I hope this overview gives you a sense of the diverse range of loss functions available. Once we've chosen the appropriate loss function for our task, we can move on to training the neural network. As we mentioned earlier, training a neural network is essentially an optimization problem. The most common used method for training is the gradient descent algorithm, a first-order optimization technique. Gradient descent works by calculating the slope of the loss function and iteratively adjusting the parameters to minimize the error. Here is how it works. Gradient descent evaluates the first derivative of the loss function with respect to the parameters, indicating how the output changes when the input parameters are adjusted slightly. This iterative approach is simple yet very powerful, which is why it has become the most popular optimization algorithm for neural networks. One major advantage of gradient descent is its speed and simplicity. However, it may be challenging to tune, and many tricks for variations have been developed to improve its effectiveness. An interesting note here is modern models like ChatGPT use gradient descent-based method during their pre-training phase of their base models. Despite its simplicity, gradient descent remains at the core of training cutting-edge neural networks. Let's work through the step-by-step process of training a deep neural network using gradient descent. First, we start with the input data, which is represented here in vector format. Then we initialize the parameters of the network, such as weights and biases, with the initial guess. These initial guesses are usually random. When we pass the input data through the network with their initial parameters, the network generates predictions. Next, we calculate the loss functions, L, for each batch of data. The cost function, C of theta, is then computed as the sum of the loss functions across all batches. The training process begins by calculating the gradient, which is the first derivative of the cost function with respect to the parameters theta. Starting with an initial guess, theta 0, we compute the gradient and update the parameters to obtain theta 1. The process is repeated iteratively, like theta 2, theta 3, and so on, until the cost function phi theta reaches a minimum value. Here comes the true challenge. The modern neural networks have millions or even billions of parameters. Each neuron typically has one or two parameters, such as W and B. And when scaling up to networks with millions or billions of neurons, the number of parameters become massive. As the result, the gradient vector, essentially a vector of derivatives, can have millions or billions of elements. Computing such a large gradient vector at each step is computationally intensive, presenting a significant challenge in training large-scale networks. This issue highlights the need for efficient algorithms and hardware to support these computations. Now we come to one of the most important concepts in neural networks, backpropagation. This term might sound complex at first, but I found a way to simplify it. Let's start by considering the simplest possible neural network, where we have just one neuron in each layer. Even with this simple case, we can begin to understand the core idea. In this setup, the output y is essentially a large composite function, a function of a function of a function, and so on, built by nesting multiple inner functions. The activation function, denoted as sigma, introduces nonlinearity, while the weights w control the linear relationships. Our goal in backpropagation is to compute the gradient of the loss function with respect to the weights, partial c over partial w, so we can adjust them during training. Using chain rule, we can decompose partial c over partial w into smaller components of partial c over partial z times partial z over partial w. Since we know z depends linearly on w, partial z over partial w is straightforward to calculate. Next, we consider partial c over partial z, which can be further expanded as partial c over partial a times partial a over partial z. Here, a is the activation output, and partial a over partial z depends on the derivative of the activation function, which we know analytically once the activation function is chosen. The true challenging part is calculating partial c over partial a. The clever idea of a backpropagation is to work backward, starting from the final output and using the chain rule to propagate a gradient step by step. This approach involves two paths: a forward path where we compute output layer by layer, and a backward path where we calculate the gradients in reverse order. By combining these two steps and keeping track of intermediate results, we efficiently compute partial c over partial w for every weight in the network. Backpropagation can be thought of as a game of chain rule. By systematically recording intermediate results during the forward path, we avoid redundant calculations during the backward path, making the process computationally efficient. This powerful algorithm lies at the heart of modern neural network training. While backpropagation is highly effective, it does come with the challenges. Two major issues are the gradient vanishing and gradient explosion problems, which arise during the backward path. These problems occur because gradient in earlier layers depend on the gradient of subsequent layers. When there are many layers, small variations in gradients can compound exponentially. If the gradients are less than 1, they can shrink towards 0 as they propagate backwards, leading to the gradient vanishing problem. Conversely, if the gradients are slightly greater than 1, they can grow exponentially, resulting in the gradient explosion problem. To address these challenges, researchers have developed various techniques. For vanishing gradients, selecting appropriate activation function can make a big difference. For instance, ReLU and its variants help mitigate this issue. Proper initialization of parameters also plays a crucial role. Neither random values nor zero work universally. Additionally, skip connections, as used in ResNet, and gated mechanisms like in LSTM network create pathways that improve communication between layers. For gradient explosion, techniques like gradient clipping limit the magnitude of gradients, keeping them within a manageable range. Batch normalizations is another powerful tool which normalizes activations at each layer, reducing the risk of exploding gradients. Regularization methods such as adding penalty terms to the optimization process also help stabilize training. These techniques don't entirely eliminate the issue, but keep them manageable, enabling more efficient and effective training. Addressing these challenges is a deep and ongoing area of research in neural networks. Now we come to the fifth step of working with a neural network, evaluating the model. Once we've trained the network and obtained results, we need to assess its performance and select the best model for our tasks. This brings us to the concept of evaluation metrics. Evaluation metrics are closely related to loss functions, as both measures the difference between predictions and ground truth. However, they serve fundamentally different purposes. The loss function is like a short-term goal. It guides the optimization process during training, helping to adjust the weights at every step. On the other hand, evaluation metrics represent the long-term goal, assessing the model's final performance for the specific task. While minimizing the loss function during training is essential, it doesn't always guarantee optimal performance when evaluated with the appropriate metrics. A classic example of this distinction is the bias-variance trade-off. As the complexity of a model increases, its bias typically decreases. While its variance increases, the optimal performance lies at a balance between these two extremes. The choice of loss functions and evaluation metrics depends on the specific task. For regression problems, metrics like mean square error MSE or mean absolute error MAE are commonly used. For classification tasks, we might use loss functions like cross-entropy loss or focal loss, but evaluation metrics such as accuracy, advanced score, AUC-ROC, or precision record curves are more relevant for assessing the results. In unsupervised learning tasks like clustering, loss functions might include k-means, triplet loss, or contrastive loss, while evaluation metrics like a silhouette score, adjusted RAND index, or normalized mutual information help measure clustering performance. For image generation tasks like GANs, loss functions such as weather stain loss are used during training, but evaluation metrics like the Frechet inception distance (FID) or inception score assess the quality and the diversity of the generated images. I don't have time to dive into all the details of these metrics, but the key takeaway is that selecting appropriate evaluation metrics requires domain knowledge. It is essential to understand the task deeply and choose metrics that align with the ultimate goal of your project. Having completed the second big question about how neural networks work, let's move to our third question. Why are neural networks so powerful today? If we reflect on the enormous attention neural networks are receiving, we can trace their success to their unique bottom-up approach to building artificial intelligence. For a long time, many experts believed that essential intelligence must originate from human knowledge, injected directly into AI system. This approach, known as top-down AI, relies on embedding prior knowledge through methods like expert system, rule-based finite state machines, or symbolic regression, etc. In this framework, deep learning is often seen as just a subset of machine learning. However, deep learning has gone far beyond the traditional machine learning techniques. Its bottom-up approach constructs models that can learn directly from data without relying on pre-encoded knowledge. This idea, known as connectionism, emphasizes the ability of neural networks to automatically extract patterns through simple arithmetic operations. Today, connectionism seems to have an edge over rule-based AI in terms of scalability and adaptability. By learning directly from data, neural networks can process far more information than traditional methods. This bottom-up approach may feel mysterious and even uncomfortable especially with the black box nature of neural networks. But it's hard to argue with the results. Tools like ChatGPT showcase just how powerful and intelligent these systems can be. As we explore this topic, I hope to spark some ideas and discussions about the underlying magic of neural networks. One of the key principles behind the success of neural networks is that simplicity often works best. Instead of introducing overly complex models, researchers have found that straightforward designs are often the most effective. For example, we might ask, why not use quadratic neurons or polynomial neurons instead of the standard linear ones? A quadratic neuron might have the form w times x squared plus b, while a polynomial neurons could involve higher order terms. While these designs could in theory capture more nonlinear features, they come with several challenges. First, there is the issue of computational complexity. Simpler models allow for faster forward and backward propagation, making training more efficient. Second, while higher order neurons might offer more expressive power, this can often be achieved just as effectively by combining linear neurons with nonlinear activation functions. Finally, more complex neurons often introduce optimization difficulties, such as severe gradient vanishing or exploding problems, which can make training unstable. Considering these factors, the standard approach of using linear neurons, a weighted sum plus a bias, and relying on the activation function for nonlinearity has proven to be the most practical and effective. This simplicity not only reduces computational overhead, but also makes optimization more manageable, ensuring stable and efficient training. Another key to the success of neural networks lies in the choice of activation functions, particularly in how they introduce nonlinearity. Initially, researchers use activation functions like sigmoid or hyperbolic tangent, which involves exponential calculations. While effective, these functions came with computational challenges, especially for large-scale networks. A breakthrough came with the introduction of the rectified linear unit, ReLU. ReLU is a piecewise linear function defined as f of x equals to the maximum of 0 and x. In simpler terms, if the input is less than 0, the output is set to 0. Otherwise, the output remains unchanged. This simplicity provides several benefits. First, ReLU eliminates the need for computationally expensive exponential calculations, reducing complexity to a simple max operation. Second, it enables sparse representations, allowing some neurons in the hidden layers to output true zero values, which is particularly beneficial for representation learning. Additionally, ReLU's linear behavior makes optimization much easier and help avoid the vanishing gradient problem that plagued earlier activation functions. Its simplicity also aligns well with modern hardware advancement, such as GPUs, enabling efficient forward and backward propagation. While simplicity often works best, it also presents intriguing challenges, especially in optimization. Neural networks typically rely on gradient descent, a first-order optimization algorithm, to minimize the cost function. However, first-order methods are not guaranteed to find the global minimum, as they can get stuck in local minima. In simpler cases such as one or two dimensional problems, it is much easier to visualize how the optimization process might fail to find the desired solution due to the bumps or complex surfaces. But in three-dimensional or higher dimensional spaces, the optimization landscape becomes far more complex, making it exceedingly difficult to locate a global minimum or even a near optimal solution. This inherent complexity highlights one of the toughest challenges in training deep neural networks. For those with a background in physical sciences or mathematics, higher order optimization algorithms might seem like a promising alternative. Methods like Newton's method, which incorporate second order derivatives, can converge faster and require fewer iterations. These algorithms also involve fewer hyperparameters and work well for moderately high-dimensional models. There are also methods like a conjugate gradient, which lies between first-order and second-order methods, offering a balance of simplicity and efficiency. Additionally, recent advancements in AI have introduced techniques like a natural gradient descent, which uses a chronic factored approximate curvature (KFAC) to improve optimization. These methods show promise in certain scenarios. However, despite these advancements, first-order methods like a gradient descent remain the most widely used and effective optimization strategy. One of the most frequently asked questions is how first-order methods like gradient descent avoid poor local minima. The answer lies in the use of stochastic sampling. Instead of calculating the loss function for the entire dataset at once, stochastic methods randomly sample subsets of data or mini batches during optimization. This randomness helps the algorithm escape bad local minima and explore a broader range of solutions. Stochastic gradient descent (SGD) has become the backbone of modern optimization. Many variations of SGD incorporate enhancement such as momentum, which smoothes the optimization path, adaptive learning rates, or a combination of both. Methods like ADAM, which adaptively adjusts learning rates for each parameter, have become the default optimization algorithm in many research libraries. At its core, the success of first-order methods and stochastic sampling demonstrate that simplicity often works surprisingly well. Despite their apparent limitations, these techniques are remarkably effective for a wide range of data analytic tasks. One fascinating finding about neural networks is the observation that more parameters often lead to better performance. Earlier, we discussed the classic bias-variance trade-off, which suggested that increasing model complexity can decrease bias but increase variance, with the optimal point lying somewhere in between. However, when it comes to over-parameterized neural networks, researchers have found a new regime known as double descent. In this double descent behavior, if the number of parameters is far fewer than the amount of training data, the network operates in the under-parameterized regime, where the bias-variance trade-off holds. But as the number of parameters increases beyond the amount of data, the network enters a new regime where having more parameters actually improves performance. This phenomenon defies the traditional understanding of overfitting. To illustrate this, one of the astrophysicists conducted experiments using only 20 data points and fit these points with models of varying parameters 4, 6, 20, and 36. When the number of parameters equaled the number of data points, traditional overfitting occurred. However, as the parameter count increased well beyond the data points, overfitting diminished, and the model started to generalize better. While it is difficult to fully explain this phenomena, especially in a network with billions of parameters, it offers insight into why large-scale models like those used in modern AI perform so well. Another compelling reason why more is better lies in the founding of approximation theory. which shows that neural networks have significant advantages when dealing with high-dimensional data. When approximating data with traditional polynomial models, the error decreases proportionally to the number of parameters raised to the power of 1 over dimensionality. This means that as the data's dimensionality increases, the number of parameters required grows exponentially. However, neural networks exhibit a unique property. They do not follow this exponential dependency on dimensionality. Instead, they maintain efficiency even as the data's dimensionality increases, making them highly effective for approximating complex, high-dimensional datasets. A real-world example of this advantage comes from the Supercomputing Conference 2020, where a group presented a framework called Deep Potential Molecular Dynamics, DeepMD. This system combines deep learning with high-performance computing to model potential energy surfaces in molecular systems. By leveraging neural networks, they achieved ab initio accuracy for systems with up to 100 million atoms, something that would have taken decades to accomplish with traditional methods. This groundbreaking work earned them the 2020 ACM Gordon Bell Prize, highlighting the unique capabilities of neural networks in tackling high-dimensional, computationally demanding tasks. Another remarkable observation is the discovery of scaling law in neural networks. Researchers have found that as neural networks grow larger and larger, their performance improves, sometimes in surprising and nonlinear ways. Initially, scaling up a model leads to incremental improvements in tasks like arithmetic operations, word context understanding, and language comprehension. However, after the model reaches some critical size, a sudden emergence might occur, where its capabilities leap dramatically. For example, these leaps might manifest as significant improvements in understanding complex language structures or performing tasks that were previously out of reach. This phenomenon, often described as an epiphany moment, explains why modern large-scale methods like models like ChatGPT have shocked and fascinated researchers and users alike. These emergent capabilities are not fully understood yet, adding to the mystery of scaling laws. Interestingly, while scaling laws have held true for many models so far, there is some speculation that they may not always apply. For example, discussions around GPT-5 suggest that scaling alone may not yield the expected performance improvements. Despite this uncertainty, the leaps observed in existing models highlight the profound potential of scaling neural networks to uncover new capabilities. These findings reinforce the notion that more is better, at least for now. Finally, we come to the last section of my today's talk. Since time is limited, I will go through this topic pretty quickly. The first question is deeper always better? This has been a point of debate in the neural network community. In October 2023, a paper from Nature proposed the shallow brain hypothesis. While I'm not a neuroscientist, the findings from this Nature paper seem to align with observations in deep learning. For example, skip connections as used in residual networks help flatten hierarchical structures, leading to significant performance improvements. This raises the possibility that deeper networks might not always be better. There's also an ongoing project called the Southern Brains, which involves using distributed systems and CPUs to run multiple small and shadow neural networks instead of a single large ones. This result suggests that in some cases, shallow networks may outperform deeper ones. This is still an open question, but it challenges the assumption that deeper always equals better. Another intriguing question is whether backpropagation, the backbone of modern neural networks, mirrors how learning happens in the human brain. Biologically, it seems unlikely that our brains use backpropagation as it is implemented in artificial systems. Jeff Hinton, often called the godfather of deep learning, has proposed alternative algorithms that deviate from backpropagation. These include forward algorithms and local updates, which aim to mimic biological learning more closely by avoiding the non-local computations required in backpropagation. While promising, these approaches face challenges in tasks requiring high performance or generating negative data. This remains an area of active research and a fascinating question for future exploration. How does the brain propagate information to learn? Many neural networks today are based on Macaulay-Pitt's MCP neural model, which was foundational to the field. However, there are several notable variants that extend or modify the MCP framework. One example is capsule networks, proposed by Jeff Hinton. These networks introduce vectorized outputs, dynamic routing, and spatial hierarchies, addressing some limitations of traditional MCP-based networks in tasks like image recognition and object detection. Another variant is GasNets. It integrates gaseous neural modulation, making them more biologically realistic. Similarly, spiking neural networks incorporate event-driven computation and temporal dynamics, mimicking the firing mechanisms of biological neurons. A more recent development is the Fourier analysis network, FAN, F-A-N, which incorporates a Fourier series using cosine and sine functions to enhance periodic information processing. This design is particularly effective for tasks involving frequency domain data. Each of these variants demonstrates the flexibility and adaptability of MCP-based networks in addressing specific challenges. Well, many neural networks are based on MCP neurons. Others follow entirely different principles. One notable example is a Kolmogorov-Arnold network called CAN, K-A-N. The key difference between CAN and MCP networks is where the activation function are applied. In MCP network, the activation function operates on the nodes while the weights are on the edges. In contrast, CAN applied activation functions to the edges with additional operations on the nodes. CAN networks are based on the Kolmogorov-Arnold representation theorem, which provides a different mathematical foundation from the universal approximation theorem used in MCP networks. This foundation gives CAN network certain advantages, including improved accuracy and better interpretability compared to traditional MCP-based networks. There is much more to explore, but we don't have time to cover everything in depth. From a practical perspective, we can implement neural networks using tools like scikit-learn, PyTorch, or Keras, leveraging Python and other libraries to simplify the process. These frameworks allow us to experiment with various architectures and applications. On a broader level, some researchers are exploring how neural networks can combine bottom-up and top-down approaches, potentially helping us achieve a deeper theoretical understanding of artificial intelligence. This is a vast topic with implications across many fields, If there is enough interest, I would be happy to prepare a future talk or workshop to dive deeper in these areas. For now, I'd love to hear your thoughts and feedback. Please fill out the workshop survey to let me know what you think or suggest topics for future discussions. Thank you so much for your time and attention. I'll stay on Zoom for a while to answer any questions or discuss further. I'm stopping the recording now. Thank you again.